All right. Good evening, everyone. Welcome to the Leitner Observatory Tuesday night public night live stream. It's cloudy tonight, so won't have the chance to do any observing with telescopes. It's cloudy and windy and a little bit chilly. Typical New Haven spring weather. So I am here actually at my house. I'm at home. Hi, everyone. I'm Dr. Michael Fesa, and I'm the director of the Leitner Observatory and also a lecturer in astronomy at Yale. So welcome to people who have been here before. Well, hello to everyone watching the recording after the fact. And what I'm going to do tonight is talk a little bit about what's up in the sky this week. And then I'm going to bring on our guest for tonight, which is Malena Rice, who is doing planetary science looking for new planets in the solar system. So we'll hear all about that in just a few minutes. If anyone has any questions as I'm talking, feel free to type out your questions in the live chat. I'll try to keep an eye on the live chat. And I will, as soon as I see your question, I'll try to make time to answer it. As I was setting up earlier tonight, I saw a really beautiful sunset through the observatory webcam. So I threw that up, and then just before going live on the stream, it got dark enough out there that the camera switched from visible light to near-infrared light. This is typical of security cameras, that they are color cameras during the day, and then at night they switch to near-infrared. And it's not really dark, too dark to see the trees and the grass and so forth out in the gardens. And the trees are very reflective in near-infrared, so the leaves look white, typical of near-infrared photography. So it's still actually a very beautiful scene, even though the sun has gone down and the sunset's over. How's everyone doing tonight? Had a chance to go out and see the supermoon last week, or actually, it was 2 weeks ago, because I think today is a new moon. Yeah, today is actually the new moon, and then 2 weeks from today, there's going to be a total lunar eclipse. Not visible from New Haven, though, but visible out on the West Coast. So should be a live stream for that from one of the observatories out west, like Lowell Observatory or Mount Wilson Observatory. So interesting to see if anything happens there. Okay, well, let me switch over to my browser here and talk a little bit about what's up in the sky this week. Here we go. So as usual, I like to go to skymaps.com and take a look at their monthly sky calendar. And they provide a really nice star chart and a day-by-day list of events coming up that month, as well as interesting things to look for with the naked eye and also with binoculars if you have binoculars. So here's the version for May, and I'm seeing all of my favorite late spring constellations. So here's what the sky looks like early May at 10 p.m., late May at 9 p.m. So we see different parts of the universe as the Earth is orbiting around the sun. So by the end of May, we'll be 1/12 of our way around the orbit. So stars that we see, rising at a particular time will be 30 degrees further to the west at the same time by the end of the month. I still see some of the early spring and late winter constellations, such as Gemini, low in the west at sunset. Cancer is not really visible in New Haven, lots of faint stars. But then Leo I think of as a spring constellation. So Leo is easy to find, sort of southwest. It's easy to recognize because of the front of Leo being this backwards question mark right here with the bright star Regulus at the bottom. And then here's the back of Leo, this right triangle with the bright star Denebola at the very back. It's actually a good place to start this time of year at sunset is to find the Big Dipper. So the Big Dipper is not quite overhead at our latitude, a little bit north of overhead at sunset. Big Dipper is easier to find. These are the 7 bright stars in the constellation of Ursa Major, right, the Great Bear. I always like these little pairs of stars here that make up the feet of the Great Bear. But the 7 bright stars in the Big Dipper you can use to find other stars. You can use the 2 stars at the end of the cup to find Polaris, the North Star, which is always right there. No matter what time of day, no matter what season of the year, it's always right there due north. And then you can also use the handle of the Big Dipper to find the bright star Arcturus, which is quite high in the sky. Arcturus, except maybe Vega if it's late enough in the evening, Arcturus is going to be the brightest star in the sky. So Arcturus is this bright red star. It's a little bit east of due overhead. And then Vega is a bright blue star that's sort of over in the east-northwest direction at sunset. Vega is part of the summer triangle. So I see 2 of the stars in the summer triangle here, Vega and Deneb. And then Altair is the bright star in Aquila the Eagle, which is sort of over here a little bit below the horizon. Lots of star clusters along the plane of the Milky Way, which is right across here. And then a few nice globular clusters over in this direction. We have actually the center of the Milky Way rising a little bit later in the evening, rising around 2 a.m. or so this time of year. And then lots and lots of galaxies, as I talked about last time, between Virgo and Leo in the Virgo cluster. Next time we get a nice clear night, I want to set up our 16-inch telescope to do some more galaxy observing. Last time we looked at, I think we looked at M101 and we looked at M51 at some point, and NGC 2903. So we'll do some more galaxy observing a little bit later on. Now, in terms of events coming up this month, we already went through the Eta Aquariid meteor shower, so that was last week. Yes, today's the 11th, new moon at 7 p.m. UT, so that would have been middle of the day today. Also on this day, moon is at apogee, so that's interesting. So that's when the moon is furthest away from the Earth in its orbit. So if we have a full moon at apogee, we say that it's a mini moon. It's a little bit smaller than average, about 10% smaller than average. And if we have a full moon at perigee, when it's closest to the Earth, we say that it's a supermoon. I don't know how super it really is. You know, it's a little bit bigger than average, about 10% bigger than average, but that's become an event that people keep track of. So 2 weeks ago, we had a supermoon, and then in 2 weeks from today, we'll have a lunar eclipse, and that will be a lunar eclipse supermoon. So I guess we'll have to call it a super blood moon again, since when it's also become a trend to call a lunar eclipse a blood moon, because the moon will turn blood red. That is also on the calendar here. Yeah, here we go. Total eclipse of the moon on May 26th. So this lunar eclipse on May 26th is really only visible from the west coast and maybe the mountain time. We have the total part of the eclipse happening starting around 2:30, 3 a.m., right, when the moon's going into the dark part of the Earth's shadow. There is the beginning of totality at 4:11 a.m. So that's going to be 7 a.m. East Coast time, New Haven time. So the moon's going to be right on the west horizon. So if you're up early or staying up late on the night of the 26th, the night of the 25th, morning of the 26th, you might notice the moon getting darker as it sets if you have a nice clear view of the western horizon. But by the time the moon is in totality, it's going to be set for us here on the East Coast. So we really won't get to see much of a lunar eclipse. But that's nice. One of 2 lunar eclipses in 2021. Let's see, was there anything else that I wanted to point out? I guess one other thing I want to point out is that this week could be a good time to look for the planet Mercury. So Mercury, the planet that's always closest to the sun. So it's going from one side of the sun to the other side, from one side to the other. If you know when to look, you have the chance to see Mercury with a naked eye. So let me actually show you this in my sky simulator here. So let me bring that up here. All right, so I'm going to this program called Stellarium that I've used many times to simulate the sky. So here's what the sky would look like tonight if it were actually dark. And so if we look over here to the west, there's the sun setting right there. Now I have a tree in the way in my simulation. I can make that disappear. So there's the sun going down below the horizon. There's the planet Venus which is going to be getting higher and higher each night at sunset, all through the summer into the fall. And there's the planet Mercury right there. Now that's about as far away as Mercury gets from the sun on that side of the sun. So there you see where it is relative to the sun. So if you do have a clear view of the western horizon, you do have the chance to see Mercury this week. And then it's going to get a little bit higher, and then eventually it's going to start going the other way, back around the front of the sun. And we say that when this happens, Mercury is retrograde because it's going backwards relative to the motion of the sun, and you're going to see it in the morning sky about a week later. So that's going to start happening around, let's see, it looks like it's going to be towards the end of May. So we have most of the month of May to potentially catch Mercury. And in fact, so there's the sky today. There's May 11th. There's the moon and Venus right next to each other, but really hard to see. And then there's Mercury and the moon right next to each other on the 13th. Actually, I think it's supposed to be more clear this later in this week, like Thursday, Friday. So I think I might actually try to observe this from the observatory parking lot, where we have a relatively clear view of the western horizon looking out over West Rock from Prospect Street. So very, very young crescent moon right next to the planet Mercury, due west right at sunset on the evening of May 13th. Okay. Let's see. Oh, Dave's saying we're watching Mercury and Venus in the western sky after sunset. So you're out in Arizona, right? So you have a nice clear view of it out there. Yeah, I'm jealous. Yeah, I think we have a chance. I think we have a chance to catch it. It's not a super favorable elongation. Sometimes it's a little bit higher in the sky at sunset, sort of depending on the season. And because Mercury has a fairly elliptical orbit, it's not a very circular orbit. Sometimes we see it at maximum separation from the sun when it's at perihelion, in which case it's quite close to the sun, only 18 degrees away from the sun. And sometimes we catch it at maximum elongation when it's at aphelion, so it's about 22 degrees away from the sun. And I've seen it probably half a dozen times in my life of actually trying to go see it. So it's not easy to catch, but if you want to see all of the 6 naked eye planets with your naked eye, and Mercury's on the bucket list to check off, definitely this is a potential to do it. Let's see, with all of the light pollution in New Haven, has Yale ever considered relocating an observatory to somewhere in Litchfield County? Yeah, actually, many people know that for a long time Yale had an observatory near Bethany, Connecticut, at the Bethany Observatory, which is a relatively dark site, certainly dark compared to New Haven or Leitner, but a little bit out of the way, a little bit hard to get to for students to get to, not for astronomers to get to. Once Yale astronomers started using other research telescopes in Chile and Arizona and Hawaii and California, Bethany wasn't really used as a research observatory anymore, and it's a little bit too far away to be useful as a teaching observatory. But we could potentially have a remote observatory that's operated remotely, and we're looking into setting up a remote observatory. A couple of different sites we've considered in Connecticut and also Vermont for a remote observatory for teaching. There's some fun projects that we could do, that some of our students could do in our labs for remote observing if we had a robotic telescope at a dark site, but not too far away. You know, not out at Flagstaff, not out at Lowell, or not out in New Mexico, but you know, an hour or so drive from New Haven, so that students could go out and do observing there or work on the hardware and so forth. So we're working on a couple of ideas. We actually we have a collaborator at Hotchkiss School, which is in Lakeville, Connecticut, and the skies are really dark there. So we may be able to do something with that. Okay, well, I think we're ready to bring on our guest speaker. So I'm going to invite Malena Rice to join me here. Let's see if we can switch over, and let me turn on her mic. Hi, Malena, how are you?
Hey, doing well. How are you?
Great, let me adjust you here a little bit here. Malena is a PhD candidate here at Yale in astronomy, and is any of you who have been to the Leitner Observatory over the past couple of years may well have seen her present a planetarium show. She's one of our superstar planetarium show presenters and has done a lot of different outreach programs at the Leitner Observatory and other astronomy programs. You were one of the main people running Astronomy on Tap, if I remember correctly.
Yeah, I've been the main coordinator for the past 3 years. Um, but now I'm stepping down, so not
Uh,
anymore, but for a while. Yeah.
Yeah, fantastic program. If for those of you who haven't heard of it, watch astronomy news or watch the Yale Astronomy News to find out announcements about Astronomy on Tap. Guest speakers who come and talk in a very informal setting in a bar. Although I
Yeah.
presume that this past year there was an online variant for Astronomy on Tap, but hopefully in the not too distant future we can get together again and drink beer and talk about astronomy. Likewise, meet at the planetarium and have planetarium shows.
Yeah.
So Malena has a lot of experience in teaching, a lot of experience in both informal and formal education and outreach. So we're really fortunate to have her here to talk mostly about her research, although she's certainly happy to take other questions if anyone has any related questions. So I'm going to hide myself and turn things over to you, Malena, and we'll hear all about your search for Planet 9.
Awesome. Thank you, Michael. And thanks everyone for being here. It's really exciting to talk about my research in this setting because I've sort of talked at Leitner about not my research, just about, space being cool in general and different things in the sky for planetarium shows, but have not yet actually shared my research with that audience. So it's cool to be able to talk about the topics that I'm most excited about and what got me into astronomy and what really motivates me in continuing and doing astronomy for a career. So I'm going to share some slides and talk through some of, well, the main project I'd say that I've been working on recently, which is looking for this ninth planet in the solar system. So I think this is a really cool idea, which is that, there are these planets that we learn about in elementary school that are the ones that consist of the or that comprise the solar system. But we don't necessarily think so often about, what if there were more? What if there were others that we haven't found? It kind of seems like since the planets that we know of were found so long ago, most of them were found, hundreds of years ago. Maybe we should have found all of them already if there were others that existed. But it actually turns out that that's not necessarily true, and there might be planets out there that just haven't actually been discovered. That are in the solar system. So we've also found lots of planets that are outside the solar system at this point, which I think is also really exciting. That's taught us a lot about what planetary systems can look like. But there's sort of this outstanding question also of, what else exists in the solar system that we haven't yet actually figured out and that we haven't actually discovered yet. So I'm going to be talking about this idea of a proposed ninth planet that's called Planet 9 in the solar system. It's kind of a theoretical planet, so nobody's ever actually observed it. But I'll talk about why we think that it might actually be there, some efforts that I've been going through to try to actually discover this planet and see if it's there, or to at least try to figure out what bounds we can put on what we think would exist in the solar system, what still hasn't been discovered. And yeah, just sort of generally talk about Planet 9 and what exactly that idea is. So our classical image of the solar system is a pretty tidy one that looks like this, where all the planets are kind of in one row here. And this is kind of an oversimplified image. It doesn't have the asteroid belt. It doesn't have the moons that exist around a lot of these planets. There are definitely simplifications to this picture, but there are actually a lot of ways that this is actually a pretty accurate picture, where all these planets are shown to not perfect size scale, but kind of relatively the sizes are about right. They actually all are roughly within the same orbital plane. So they pretty much lie in this one disk, and they are all orbiting together in this roughly 2D plane with a little bit of inclination in there, but not much. So we have this nice image where we think the solar system formed in this nice, pretty disk that surrounded the sun. They all formed in the same disk, and that's why they all have these very similar inclinations to each other. And they moved around a little bit in and out, but we don't think that anything too dramatic would have happened there. Maybe you might have tossed a planet or two out, and that's definitely possible. That's actually not something that we're able to say with definitiveness just yet. And if Planet 9 exists, maybe it would have been something that was tossed out from the inner solar system. But the planets that we have right now, they look like they haven't really gone through any very dramatic interactions. They haven't been sort of dramatically affected by anything in particular that would cause them to have different angles relative to each other or other configurations. But then there's a lot more to this picture, again, that hasn't been totally encapsulated with the simplified picture. And in particular, there's a lot that's been unraveled in the outer solar system over time that isn't very well explained by our current understanding of the solar system. So if you start looking outside of Neptune's orbit, if you start considering all these populations in the very, very distant solar system, there are a lot of kind of weird properties of the objects that you find out there. So this picture is just showing the inner 30 astronomical units of the solar system, where the known planets lie. And an astronomical unit is the distance between the Earth and the sun. But if you start looking outwards, then you're going to start finding some additional things that aren't so well explained in this very classical picture. So this image here is showing the orbits of the known extreme Transneptunian objects. And I mentioned earlier that the image we were looking at was 30 astronomical units. And that's the radius of this little red circle here. So all of that solar system exists within this little red circle. And if you zoom way out, then you can find these quite large asteroids that are on these orbits that are completely outside the solar system. So these are some of the most distant objects that are known in the solar system. They're called extreme Transneptunian objects. And they're sort of extreme because they have these weird non-circular orbits. They tend to be on these really elongated orbits, like what you see here, where they're not circles. They're sort of stretched out ellipses. And their orbits often lie entirely outside of the solar system. So they're not really directly interacting with the solar system planets in many cases. They're sort of completely external to the solar system. They're just doing their own thing, totally outside, not really having anything to do with the stuff that's interior that we're more accustomed to studying. And something that is really weird that has been observed about this population is that a lot of these orbits seem to be preferentially angled in one particular side of the sky. And you can see that here where all of these orbits are kind of angled towards, I guess, either the left or the right, depending on how you look at it. And there aren't really any orbits that are facing the other way. And that's something that's really weird because over time, we expect orbits to sort of spread out over the entire solar system. So none of the orbits actually perfectly closes. They're actually not perfect ellipses. They sort of end up sort of processing all the way around the solar system over time, where they're not going to stay static. Orbits are continually changing because they're interacting with each other, potentially with other stuff that's in the solar system, although these ones are kind of more external to the giant planets, so they're less likely to interact with those, but they're interacting with each other and with other stuff that is outside in the distant solar system. And so they shouldn't really be clustered on one side of the sky. We really would expect them to be all the way around the entire sky. We should see them everywhere that we look. But that's not what is observed. And this is interesting because it's not only been found that they tend to be clustered in terms of this angle where the orbits are kind of angled in one particular direction, but they also are preferentially in one plane of the sky as well. So this is hard to see in 2D because, when you're looking at different planes, it's kind of a 3D question of, do the planes line up this way or are they perfectly aligned this way? But they all tend to be in roughly the same plane, and it's not the same plane as where the solar system planets are. And that's pretty weird because if these are all kind of outside the plane of the solar system, they're all on these really weird, highly eccentric orbits, it's not really well understood how they would have gotten there. usually when we try to explain weird orbits in the solar system, we say, oh, maybe Jupiter interacted with it and it was thrown onto this weird orbit because it got too close to Jupiter and something happened to it. But these orbits, and in particular the ones here that are in purple, are completely stable. They're these really elongated orbits, and they're also clustered in one side of the sky. So this is all sort of weird, not very well explained stuff that we don't really have a great explanation for when you just consider this classical picture of the solar system. And that first plot was from just 5 years ago or so. This has actually picked up a lot of traction recently. And so this is an updated image that shows more of these orbits, more of these objects that have been discovered, all plotted together. And in particular, what's interesting is that the stable objects are the ones that are clustered. And there are some that aren't stable, that are not sort of following the same pattern. And that's okay, because the ones that aren't stable are probably, they recently got onto that orbit and they're pretty soon going to leave that orbit, where by soon we mean maybe millions of years, which is pretty short on an astronomical time scale. But these purple ones, they should stay on those orbits for a very, very long time, like billions of years. And so it's really weird that they are the ones that are clustered, whereas the ones that are unstable, you could say, oh, maybe something interacted with them to put them on that orbit and they're just there for a short time. But the purple ones are showing this weird clustering. So this is all sort of the argument for maybe there needs to be something else that's holding them in place, something else that's providing this force that's forcing all these orbits to stay on one side of the sky. And the idea there is that there might be this other planet, this hypothetical planet 9 that's in the very, very distant solar system. It's kind of in an orbit on the opposite side of the sky, so maybe sort of similar to this upper green orbit labeled KG163. Going to be something sort of similar to that, where it's opposite to the rest of these orbits and is able to then hold them in place by forcing them all to stay on one side of the sky using the gravitational force that it exerts. And so if we, again, just return to this classical picture of the solar system and consider what this 9th planet would look like with respect to the rest of the planets, we'd have to zoom way, way out to see this planet in the first place. So to scale, this is the distances here to scale. The planet, of course, is not going to be bigger than the sun. If this planet existed, it would be very far away. So it's maybe not too surprising that we wouldn't have already seen it. Galileo wouldn't have discovered it with his telescopes. Even with current telescopes, it's actually pretty challenging to see objects that are that far away, even if they're planet-sized. And so the distance would be 400 to 800 times the distance between the sun and the Earth. So that is a lot farther than any of the planets that we know of right now. Neptune, again, is 30 astronomical units from the sun. So this would be over 10 times as far away as Neptune is. It would be 5 to 10 Earth masses, so it would be bigger than Earth, but it would be smaller than Neptune. It's not a huge planet. If it was maybe Jupiter's size, then maybe we would have seen it already, but it should be actually smaller than that. It should be inclined relative to the solar system by 15 to 25 degrees. And this might also help to explain why we might not have seen it, because usually when you try to study the solar system, you look at things that are in the plane of the solar system. You don't really look at these very high inclinations because there just isn't a lot there to study. And so usually solar system studies don't really focus on this part of the sky. So that might also help to explain why we wouldn't have seen it. And it should also be on a pretty eccentric orbit. So it wouldn't be on a perfectly circular orbit. If we want to explain how it interacts with all these other very eccentric objects, then it would also need to have an eccentric orbit just on the other side of the sky in order to interact and provide this restoring torque that is needed in order to keep all those other objects put on one side of the sky and stay on its other side of the sky. And so these are the properties that we would expect for this hypothetical planet if it exists. But then what do we actually know about what we should have seen already versus, what could still be out there that we haven't actually discovered? Well, if there is an undiscovered planet out there, then it needs to be some certain size and it needs to be some certain distance such that we wouldn't have already seen it. So in particular, it has to be small enough that it hasn't been detected by all sky surveys. So if it was the size of Jupiter, then maybe we would have expected to have already seen it, especially if it was relatively nearby. And so that's one constraint that you can say, it has to be smaller than a certain size so that we wouldn't have observed it already. It also has to be big enough to be considered a planet if we want to say that it's an undiscovered planet. And so this is a semi-arbitrary lower limit, but it's basically just set by the definition of a dwarf planet, which is a planet that's large enough to clear its orbit, and is also large enough to maintain hydrostatic equilibrium, which is why these planets are round. So there are a couple of different sort of technicalities that go into what a dwarf planet is, but that's what sets this lower line here. It has to be close enough that it wouldn't have been thrown off of the solar system when the sun was first born. So the sun probably was born in a cluster of stars. There were probably a lot more nearby stars when the sun first formed, and those stars sort of interact with each other a bit. So they sort of fly past each other and have these interactions that are going to be stronger if the stars are closer together or weaker if the stars are farther apart. And so if you had a planet that was too far away, then it would have just been tossed out of the system when another star got too close. So you need to have it be close enough that that wouldn't have happened statistically if we just consider the type of environment we'd expect the sun to be born in. And it also has to be far enough that it hasn't led to detectable perturbations on the solar system planets. And what that means is that it can't have affected the locations of all of the current planets enough that we wouldn't have seen it. So we know the positions of a lot of objects in the solar system to pretty high precision, in particular the spacecraft in the solar system. We know where they are to pretty good precision in order to make sure we're continually contacting them. And if you had a planet that was too close by, then its gravitational force would alter the location of those spacecraft, and you would be able to actually see that effect. And so you're able to put this lower limit on how big it could be or how far it could be based on this effect, where it can't be leading to these perturbations that we just haven't seen. And so the way that I am searching for this planet is using something that's called the Transiting Exoplanet Survey Satellite, which is a spacecraft that was not designed to look for Planet 9. It was actually designed to look for new extrasolar planets around other stars. But the spacecraft is actually really great to look for Planet 9 because it searches the entire sky in its survey. So it has these 4 cameras that you can see here, and they sort of sweep around the sky, first looking at the entire southern hemisphere, and then flipping upwards and looking at the northern hemisphere. And this gap that's in between the southern and northern hemisphere is the orbital plane of the Earth, which is pretty similar to the plane of the solar system. And so this 9th planet, if it exists, we'd expect it to be outside of that plane. So this gap that is not observed is exactly where we wouldn't see the planet, and everywhere else is observed. So if the planet exists, it should be somewhere within this data set. Also conveniently, TESS happens to align its cameras really nicely with this ecliptic plane of the solar system. So all those cameras are aligned parallel to the Earth's orbit. What that means is these really distant objects that are so far away that they just look like they're static, kind of like the way that stars often just look like they're static. They aren't actually moving very much on their orbits over the time that TESS is observing them. We're just seeing the Earth move past the object. And so for a distant object in the solar system, when you see the Earth move past it, it just looks like it's passing on a straight line along the Earth's orbital direction. So you're just seeing Earth move past, there's an object there, and it looks like it's just going on a straight line across your image. And so that really means that there aren't actually that many places that we'd have to search. There aren't that many orbits we would have to check. We just need to see if we can find a bright point that's moving on a roughly straight line across the detector that is consistent with the distance of Planet 9 that we would expect from these previous models. So what we're looking for then is basically, and this is just an image from that data set, a dot that's moving across our image like this. And so that's just a planet that's moving across the image on a pretty straight line. There's a little bit of motion in the up and down direction, but it's mostly going left to right here. And the way that we can search for this type of object is by actually just shifting the image past instead and adding up the signals of these pixels where we expect the object to be and seeing if we can find that signal. So sort of equivalent to what we had seen in the previous slide, you can just slide the image past instead in order to try to figure out if there is an object there. And you can just follow the frame of the object. So that's sort of what we're doing in this search. We see there is an object that is moving through the sky in some particular direction. And you can consider like the path that you expect the object to be on. And then you can do some data reduction to just get rid of stars and other asteroids and things in the image that aren't the object you're looking for, and just leave everything else that hasn't been discovered. And if you remove all those other signals and then add up your images along the path of that object that you expect to find, then you can get a nice signal like what we see on the right here. So this is an actual recovery of one of those extreme Transneptunian objects called Sedna. It's on one of these really extreme orbits. It is one of these super crazy objects that isn't very well understood that's in the outer solar system on an orbit not too dissimilar to what we'd expect for Planet 9. And we're able to recover the object or the signal of this object, which is totally impossible to see in this first image. Sedna is actually within these white circles at different points in time, and you're not going to be able to see anything in this image. And so it's just showing where it is at different points. I think in this particular frame, it should be maybe somewhere in the middle here. And once you do all this data reduction, you can actually pull out the signal of this object, even though it's impossible to see in the raw frames, because you can just add together all of the data that was taken by TESS, which is usually about a month for each part of the sky. So with that, you're able to pull out the signals of extremely dim objects like what we would expect for Planet 9. This video is showing another way to think of that, where this is sort of a concept that we call shift stacking, which is where you start out with your image and you add the images up while shifting the images along the path of the object that you're trying to recover until you end up with a signal for the object that you'd like to see. So here, this is actually Sedna. That's the extreme Transneptunian object that I mentioned on the previous slide. And you're starting out with this big empty gap on this image on the right that ends up getting filled in over time as you sequentially shift and stack the images that show up on the left. So just to recap, the image on the left here in this video is just showing basically a video of a part of the sky. You're seeing different asteroids as they pass through the frame. This is just, you masked out the stars here and you just see asteroids passing through. And if you shift and add together the images along the path of a real object, then you can get a nice signal like what we're seeing here. So this is a nice way that you can recover these objects that would otherwise just be completely lost in the noise. They totally just blend in with all of the noise everywhere else in the detector, and they just look like they don't exist unless you're adding up the signals from hundreds of different images in order to actually recover the signal of that object. So I think this video is probably going to be kind of staticky on your screen, and so you can go to this website as well if you want to see it sort of in its full glory. And so this is the idea of shift stacking, which is you consider a path of interest, you align all your frames along that path, and then you just add them together and see if you end up with a nice signal that comes out of it. Something else that we do in order to look for undiscovered objects, because that works really nicely. If you know where the object is, you can just follow its path, make sure you're stacking along it. But if you don't know where the object is, then you need to basically just do this along every path that could possibly exist. So we consider all of these paths that we'd expect Planet 9 to be on, and we create something that is basically just an aggregate frame that considers every possible path and just maintains the largest signals that you would get after you complete this process along all of the paths to try to figure out whether there's anything in that image, if there is just nothing there, and to try to see if there's anything in the outer solar system that we've been missing that we are able to recover in this data set. So this is just showing a couple of examples of objects that we were able to recover with this signal. So in the left column, we're seeing these objects that were recovered by shifting and stacking along their known paths. So these are all distant objects that are sequentially dimmer. So the top row is the brightest object, the middle is a little bit dimmer, and the bottom row is the dimmest. And then the left column here is just saying, we know where these objects are, we'll shift and add together all the images along that path, and we're able to nicely recover the signal of that object, which is great. We would expect to be able to see it if the data is of sufficient quality to actually pull out that signal. But then in the second two columns here, we actually don't tell our algorithm where these objects are. We just check every single possible path, and we try to see, do these objects turn up? Are we able to still find them, even though we didn't tell our pipeline anything about where they are? We just said, okay, let's check every possible orbit and see if these objects show up. And we were able to recover the two brighter objects. The dimmer one we weren't able to recover, and there are a couple of reasons for that I can talk about, but probably the simplest one is that it's the dimmest of the objects. And so the dimmer objects are always going to be more difficult, and you're always going to get more noise when you're trying to recover really dim things. So that just sort of tells us about where our limit is. But we'd expect Planet 9 to actually be about as bright as these top two columns. The lower one, it could also be that dim potentially, but most of the possible parameter space for Planet 9 is actually covered by what our pipeline should be able to accomplish. So what we're trying to do now is actually just apply this to the entire sky. We're working on implementing neural networks. So we're using machine learning to go through all of the data. There's quite a lot of data covering the entire sky. So we're creating this algorithm that is able to not only do what we showed on the previous slide, but also just do it for the entire sky, and then just spit out what are the best candidates that we're able to find. And then once we have that running, then we just need to apply it to the entire sky. And it's actually pretty close to being at the point of being fully operational now. And we'll just see what we're able to observe. And if we find anything cool, then we'll point a telescope there and see if we're able to actually find an exoplanet, which would be pretty exciting. So thank you all for being here, for listening, and I'm happy to take any questions.
All right, thank you so much, Malena. That was very interesting. Very nice project setup, and looking forward to getting results soon. If anyone who's watching the live stream, if you have any questions that you'd like to throw out, type them into the chat, and as soon as I see them, we'll try to address them. But I have a couple of questions for you. I thought Planet 9 was Pluto. Why are you doing this revisionist retconning business? Clyde Tombaugh in 1930 found the ninth planet.
Yeah, I mean, so Pluto definitely, if there were other Pluto type planets, that would also be pretty exciting. And this type of algorithm would be able to find those. Well, I suppose Dwarf Planet is technically what the IAU calls them, the International Astronomical Union. So Pluto's technically not considered a planet because it's just a little bit too small, and there are several objects like Pluto that have been found. So if you call Pluto a planet, then you have to suddenly start adding a lot of objects to your list of planets, and people don't like that. People prefer to just have a few that they have to memorize instead of like 30 that they have to memorize. So I think that's probably a big reason we're not a planet now. But yeah, depending on who you ask, it's very controversial. Some people like it and some don't.
Yeah, well, I guess we're at 8 classical planets now and 5 dwarf planets, and my son has a mobile in his room with 8 planets on it. So I thought that was very advanced, that it was only 8 planets and not any of the dwarf planets. Also, you know, I remember back in the 80s and 90s, there were people like Velikovsky and Art Bell and other like kind of quacky crackpot media people saying, oh, there's this companion to the Earth. Sometimes they called it Planet X, or there were some other names for it, Nibiru, I think, and whatnot. I'm sure you and Greg have to address this. Is this planet going to send a storm of comets into the inner solar system? You know, is this foretold by Nostradamus.
Yeah, I feel like I've heard of this. I want to say, is that the planet that is on the other side of the sun at all times?
I
And so
think
we
that's
would
one
never
of
see
them.
it.
Yeah,
So, I mean, I guess in theory, if that existed, you wouldn't really be able to see it with telescopes from the Earth. If you looked at it with like Cassini or a spacecraft that's somewhere else in the solar system, you should be able to see it.
yeah,
But back in the 80s, I'm not sure that I think we had Voyager at that time or around that time,
yeah,
but
sure. Voyager was launched in
uh,
1977, I think.
yeah, so you probably would have been able to see it, but I don't think we have too much to be worried about in terms of like storms of asteroids or anything like that from
Yeah.
these types of objects. There actually are, other than this planet nine, there are actually other distant planets that have been proposed. So some of those would be maybe smaller than Planet Nine and might also not have been discovered, but the kind of prevailing theory for how the solar system formed includes Jupiter kind of moving around a little bit in the solar system. And so the idea there is that it might have actually tossed out a bunch of embryo planets early on. So there actually might be like a Mars-sized planet out there as one of the popular ones where the if you look at the plane of the solar system, you can kind of take an average of that plane at different radii when you go outwards from the sun. And when you get far out enough, there's this weird warp that isn't very well explained right now. And if there was a Mars-sized planet out there that we probably wouldn't have seen, because that's pretty far away, we wouldn't have seen a planet that small, it would actually pretty well explain that. So that's another thing that would be pretty cool to look for with this algorithm, actually, to see, maybe there's another Mars that's way out there.
Yeah, that's really cool. That's really interesting. Okay, so let's see. Fred says that Planet Nine is hiding. That's why we haven't found it. Could be. Um,
Yeah.
T.D. Bodie asks, in the search for Planet Nine, if you were to find the planet, what name would you push for it? And if there's a chance that Planet Nine was there but was ejected is there a chance that there but it was ejected due to other passing masses? I think like you were just saying with Jupiter.
Yeah, so it could definitely be out there and have just been ejected from the solar system. Perhaps that, I mean, if it's out there, then exactly how it got to where it is like a whole other question that isn't very well explained. Um, yeah, so it's not well explained how it would have gotten there, but we've seen similar configurations in extrasolar systems. So those aren't very well explained either, but it's been shown that they exist. And so at least we know that it's possible. Um, in terms of what I would name it, I think I would need to be pretty cocky to actually get to the point where I've decided on a name. Yeah, I don't know. I don't want to jinx it. I feel like I'll never find it if I try to give it a name before. So.
Yeah, well, it seems like the discoverers get a provisional name that there have been a couple of examples like Eris was named Xena for a while. I think Mike Brown came up with that. And there are a couple of other examples. My former advisor at Cornell discovered a new moon of Uranus and wanted to name it Squeaker after his cat. But the people who decide this is the International Astronomy Union. There's a committee that decides names for things. So it probably have to be another Greek god. I don't know which one is on deck to be the next planet. But
yeah, I wonder if I picked a name that they would be happy with, if they would go with it, or if they pick one name.
Yeah.
I'm not really sure.
Fred says maybe the planet will be 9 star. Yeah, well, it probably will always have an asterisk because of the Pluto thing. Right. Planet Noble asks, how much data are you processing in your search?
It's continually growing as Tess is continuing to observe, but the primary mission is, I think it's something like 17 terabytes of data. So it's pretty big, but it's not totally crazy. So pretty soon the Vera Rubin Observatory is going to have a survey going up that's going to be observing not the entire sky because it's ground based, but it's going to be observing, I think, like 50 or 60% of the sky. And that telescope is going to have, I think, like petabytes of data every night, which is just crazy. So terabytes I'm happy to be working with. That's at least something that I can store on, maybe not on my laptop, but on an external hard drive that I just own without having to get, extra very expensive resources. Yeah, so it's a large data set, but it's not totally unbearable. It just takes a bit of time to read it in.
Yeah, neat. Yeah, I'll ask just before I let you go, I have just a couple of questions. It'd be interesting to see. So I know you're using the test data because you have this great time sampling, very frequent time sampling. So you don't know where to look for it. So you can automatically search big swaths of the sky with really good time sampling, even though it's not necessarily the most sensitive telescope. But I wonder if at some point in the future you could get James Webb telescope or some more sensitive telescope to do more targeted searches. Since you have a rough idea of where it is, you have a rough idea of which way it's moving, a rough idea of the speed if you have constraints on the eccentricity and so forth.
Yeah.
Yeah. So.
Yeah, I mean, we have a sort of rough idea of what its orbit looks like. The problem is we don't know where on its orbit the planet is. So that narrows down not a huge amount of the sky. It has to be at relatively low inclinations, but that just means it probably isn't like at the poles, of like the North or South Pole. We actually think that because it hasn't been found, it might be likely that it's just lost in the galactic plane. So the galactic plane is just, the plane of the Milky Way. If you look up in the sky in the southern hemisphere especially, but also at some places in the northern hemisphere with clear skies, you can see the Milky Way, and you can see that there are just way more stars there than everywhere else in the sky.
I see them behind you there. There's lots of stars.
Yeah, you can see it here. And so there are a lot more stars that are in the plane of the galaxy than anywhere else in the sky. So if you had a ninth planet that was in that plane somewhere, so it sort of aligned with the galactic plane, it would be a lot harder to find it because there's just so much stuff there that it could be confused with. So that's actually the main place we're looking, which is probably the hardest place to look, but that's maybe why it hasn't been found if it's there.
Yeah, and the fact that it's, like you say, it could be at aphelion, it could be really far away, moving really slowly. Yeah, that's a really good point. Fred says, thanks, Malena, good hunting. Also, have you considered a citizen science program for data analysis? EVE Online is a game that builds in real-world data where people match sets for planetary transits or something like SETI at home.
Yeah, so I know there's actually something going on for this right now, I think called Planet Hunters, that citizen scientists can go and specifically try to search for Planet 9 with that program. And there have been some published papers that have come out of that where usually what ends up being found is brown dwarfs, which are kind of between planets and stars, because they're something that can pretty easily interpret or impersonate Planet 9. They have sort of similar looking properties when you find them in the sky. But that does exist. My current pipeline of my code is just not in a place to give it to the public right now. It's just being constantly developed. And so I wouldn't want to confuse people further or give you messy code. But if I get it to a point where the code is really clean, and I'm able to make a nice interface for it, then it would be wonderful to have help for sure.
Do you have a sense of where you were showing the mass versus distance space where there could be an unknown planet? Do you have a sense of how much you cut off with the test data? Do you know where you're searching in that search space?
Sorry, I missed the first half of your question.
Oh, sorry. I was saying you had that plot in your slides of the restrictions of where an unknown planet could be in terms of mass and distance. Do you know where this project is cutting into that?
Yeah, so let me see if I can show this again.
Yeah, that's the slide I was thinking of.
Replay it. So, well, actually, I can't use my mouse if I do that, so I'll just expand this. So what we're going to be looking at is we're starting to push um, the closer distances and at lower masses. And so we're going to start sort of pushing in this direction from the left. And so we probably wouldn't be able to rule out a planet that's like an Earth mass that is 1,000 times the distance of the Earth, because that's just very, very far away. It's a very small object. But I think we should be able to start taking scoops out this way to move this parameter space outwards. And hopefully, we probably can't actually rule out the entire thing, but we should be able to rule out more of it. And I actually think it's going to be a while before we can rule out the entire parameter space with any space telescope, because unless you send something out that's pretty far away, those objects they start getting really small, or the reflected light in particular that you get from the objects is very minimal. So what you're looking at is light is actually going from the sun all the way to the object, all the way back to you. And so a lot of that light is lost in that path.
Yeah.
So the farther the objects are, you really lose light really quickly as you start looking at very distant objects.
Yeah, I was thinking about what's the crossover point where if you have an ice giant like Neptune, at what point is its infrared emission going to be more than its reflected visible light? So you might look in infrared, or even with sensitive radio telescopes.
Yeah, and I think actually the Citizen Science Project is looking in the infrared. And I know there have been some projects looking in radio, so there are lots of different types of surveys looking for Planet 9. And yeah, I've been doing sort of this optical survey because well, first of all, because you have the nice time sampling, because you're looking at the entire sky and you might as well use that data set. But also because we really don't know what this planet is going to look like. And so it's really worth looking at all these different wavelengths, because, I mean, if there's one thing that looking at the census of exoplanets has taught us, it's that planets are very, very diverse, and you can't assume that they all look like the ones in the solar system. So it's not really that clear what this planet would actually look like. It probably would be a gas giant, so it probably wouldn't have a nice solid surface like the Earth, just because it's big enough that it probably would have to be a gas giant. But I mean, we really don't know that much beyond that. We have no idea what its properties would be. So if we found it, it would be really cool, because it's a type of planet that doesn't exist in the solar system, but that's pretty common in extrasolar systems. And we don't really understand the properties of those planets because we don't have one in the solar system. So if we had one, that would be great. But maybe that's wishful thinking.
Yeah, you know, those exoplanet systems have so many things we don't have. They got hot Jupiters and, you know, all of these planets between Earth and Neptune that we don't seem to have. Maybe this is one of them. So, all right. Well, you anticipated my last question. What do you imagine this planet to be like? But yeah, that's, will we visit it someday? Will we send a space probe to it? It took long enough to get to Pluto. It's going to take a long time to get out to this planet if we can find it, if it exists.
Yeah. Yeah, I'm sure if we found it, that we would certainly send a probe there, just because there's so much that we could learn about all of the other planets in the solar neighborhood through it. It's just, in terms of size at least, it would be much more similar to those than anything else that's in the solar system. So it would teach us a lot, especially since those super Earth type planets seem to be the most common ones in the galaxy. And yet we really don't know very much about them. They're kind of a hot for sea, but to get that much information from exoplanets that are many light years away. So yeah, hopefully we'll be able to actually go there. I think it would be an amazing, amazing way to advance science relatively quickly. It would take a long time to get to Planet 9. Yeah. But yeah, it's all dependent on also finding the planet and also the planet existing in the first place. So it's certainly worthy, I think, because of the amount of information that we would gain from it. Certainly worth looking for it. But I don't know. It might be there. It might not be there. And if it's not there, then maybe we've got some other issues that we need to solve.
Yeah, you got to explain those. You got to explain those perihelion, those Sedna type objects. Something's going on there. All right, well, thank you for a wonderful presentation. Really interesting to learn about and something we can look forward to, a prediction we can look forward to. Okay, so I think we're just about out of time. So let me sign off here. So thanks everyone for tuning in for this live stream. If anyone has any questions, feel free to send me an email. My email is michael.faison, so michael.faison@yale.edu. If you have any questions about the presentation tonight or things that are coming up or what we do at the Leitner Observatory or in Yale Astronomy, I'm happy to take your questions. The Leitner Observatory has a website, which is Leitner Observatory, Leitner observatory.yale.edu. So post news there about what's going on. If we happen to see Planet 9 with our little 16-inch telescope at the Leitner Observatory, we'll let you know. Or if our students do anything fun, do any fun projects there, we'll let you know. Otherwise, I wish everyone well. Have a great weekend, and I'll see you next time. Thanks, everyone.
Right.